Hi, welcome to another video. I'm going to review the second chapter of this special publication of SCG. It's about the Western Tethyan magmatic belt. This Eocene magmatic belt records Diachronous and trench parallel migration of magmatism and metallogeny, which extends from northwest Anatolia through the Balkans. Something which I added to this review and it's not covered in the article is the importance of oblique subduction, which is quite important in terms of metallogeny. It controls the location, timing, and type of mineralization through crystal scale deformation, and also fluid pathways and melt source diversity. In structurally complex terrains, understanding how gold got there is half the battle. This study stands out because it doesn't just describe geology, it decodes the full system. First of all, the team mapped over 600 structural features, including faults, folds, foliations, all at a very high resolution, and that's a precision that you don't often see in regional scale works. Then they zoomed in, and they have done petrographic and microstructural analysis, which showed how veins and alteration textures formed right where fluids moved and deposited gold. But what's unique about this study is that they linked deformation and mineralization in time. By doing uranium lead zircon dating, they pinned down exactly when rocks folded and when gold arrived. To top it off, they used quantitative alteration indices to like AI and CCPI to track hydrothermal footprints. This means that you can spot the system even where gold is missing. With balanced cross sections and structural and restorations, the team built a true 3D view of the ore body evolution from early thrusting to late inversion. So this is more than a mapping project, it's a blueprint for understanding structurally controlled gold systems. Here we have a regional map. The Western Tethyan belt is a collage, a mixture of ancient continents and oceanic remnants. As the Neo-Tethys Ocean closed, microcontinents from Gondwana smashed into the southern edge of Eurasia, and they created a jumble of suture zones and magmatic arcs and crustal fragments. These collisions were not clean, they were messy, they were diachronous and prolonged, and then they left behind zones of weakness, like scars in the crust that could later become conduits for magmas and hydrothermal fluids. Now fast forward to Eocene, around 55 to 35 million years ago. Subduction was still underway. The Neo-Tethyan slab was sinking beneath the Eurasian plate. But here is where the story takes a twist. Instead of a steady descent, the slab began to roll back. Imagine that you're pulling a rock from beneath your feet. As the slab retreated, it dragged the arc trenchward and caused the overlying plate to stretch and thin. And this rollback was not just local, it propagated like a tectonic ripple, first in northwest Anatolia, then west into the Biga Peninsula, and then into the Rhodope zone, and eventually into the Serbo-Macedonian domain. So, as the magmatic front moved, so did the mineral systems in the region. These are cartoons that I got from another article by Yin 2012 to explore what rollback actually means and how it's different from the more traditional view of subduction arcs. In a classic volcanic arc, an oceanic plate dives beneath a continental one at a fairly stable angle. The arc, which is the line of volcanoes, remains relatively fixed above the subducting slab. These settings are dominated by compression. The crust thickens, magmas rise vertically, and the mineral systems cluster around stable trench arc, back arc geometries. Think places like Andes or Cascades or the Japanese archipelago. But in a rollback arc, the slab retreats trenchward, steepening as it sinks faster than the overriding plate can keep up. This pulls the arc toward the trench and triggers extension in the overriding plate. It's like peeling back the Earth's crust. You get back arc basins, extensional faulting, and occasionally, for us, spaces for magmas to rise quickly and cool slowly, and they may form porphyry systems. So, while both types of arcs generate volcanoes, rollback arcs are mobile, diachronous, and they are often accompanied by dynamic changes in geochemistry, heat flow, and crustal stress. So, for mineral explorers, this means one thing: follow the migration, not just the magmatism. Here is a zoomed in map of the study area. This district hosts several calc-alkaline porphyry, copper, molybdenum, and gold systems. We have deposits like Karapinar, Murat Tepe, Gelemich, and Tofik Chikonak, which in place during the early to Middle Eocene between 51 to 46 million years. These intrusions are structurally localized within the Tafshanli zone, which is located at the south of Izmir, Ankara, Erzincan suture zone, and it exhibits classic porphyry style features. We can see fault architecture plays a critical role in the emplacement and exposure of these systems. Mineralized intrusions are dominantly situated in the footwall of west-northwest trending Eskişehir fault, which is a major normal dextral structure in this region, and accommodated post-collisional extension and guided magma ascent. And we have some secondary faults, which are both strike, slip, and normal, and they further segmented the crust in this area. Here in the left image, we have a chart which shows how porphyry systems migrated west over time across the western Tethyan belt, and they extend from Turkey to the Balkans. You can see that there is a red regression line in this image. It shows a clear pattern. As we go west, the rocks get younger, and that's the Diachronous rollback. The subducting arc slab retreated trenchward, and magmatism followed with a rate of about 4.4 millimeter per year. The colored symbols represent different geological events. Each cluster, including Bursa, Biga, Rhodope, Serbo-Macedonia, they marks a time-stamped step in a westward moving arc. And this is not just a timeline, it's a tectonic breadcrumb trail which shows where and when porphyry is formed. And if you follow the timing, you follow the ore. On the right side, we have zircon uranium lead dating and argon analyzes and alteration minerals. Researchers here pinpointed the age of mineralization, and it matched it to younger porphyry systems migrating progressively to the northwest. Mineralization migrated west, just like the magmatic arc itself, and it shows the rollback in action, and it's quite rare to see it captured so clearly in the Metallogenic record. And now here's what's even more interesting. While the article doesn't explicitly propose oblique subduction, the geological patterns here line up almost perfectly with rollback-driven arc migration seen in other regions of the world. Here's another map that I got from a different article by Galhofer and colleagues, 2017. It tells a tectonic story that stretches from the Alps to the Himalayas. And what it shows is more than just faults and fault arcs. It reveals the tectonic DNA of some of the world's most metal-rich regions. And notice the pattern. We have oblique subduction. It's not your classic head-on collision. It's angled, asymmetrical, and it's messy. But this messiness is a kind of gift to exploration geologists. Why? Because oblique subduction doesn't create one uniform arc. It segments the magmatic front, introducing local variations in heat flow, stress regime, and crustal permeability. And these segmented belts become prime targets for porphyry and epithermal systems. Now, layer in the faults. We have strike slip and transtensional zones in these areas. These are not just structural oddities, they are fluid highways. They allow magmas and mineralizing fluids to ascend, pound, and react with the crust. So when you see this kind of tectonic setup, segmented arcs, oblique convergence, and strike slip faulting, you're looking at a very fertile metallogenic engine. Here we have outcrop hand sample and close-ups of samples from different parts of this study area. In image A, we have a sample from Karapinar, which is a porphyry copper molybdenum deposit. The sample shows it's showing phyllic alteration over earlier potassic assemblage. Note that the classic surcite over biotite zoning, the sharp contact between surcite and potassic zone, is unusually well preserved for a porphyry system. In image B, we have a sample from another deposit which shows a potassic altered granodiorite with quartz surcite pyrite overprinting. What stands out is the presence of potassic relics within the phyllic overprint. This partial preservation suggests a complex fluid evolution and possibly telescoping of hydrothermal events. In image C, we have a sample from Morat-Derre, which displays intense phyllic alteration and oxidation. As part of an gold uranium-rich porphyry, it's somewhat unusual in a copper molybdenum context. Usually uranium and gold enrichment may indicate a more evolved and volatile-rich magmatic source. Then we have image D from Sarichai, which is a granite with pyrite in veins and disseminations. It is common in porphyries. The textural uniformity of pyrite here may suggest fluid immiscibility or well-focused flow pathways in this deposit. Then we have image E, which is a sample from Gelemic deposit. It contains abundant cerussite, malachite, and iron oxides. The presence of tenorite here is particularly notable as a supergene mineral, which indicates a weathering overprint above copper molybdenum porphyry, and it's a textbook example of multi-stage mineralization. Then in image F, we have a sample from Oilat deposit. It shows a strong phyllic overprint, subtle but significant, or the fluid-scape textures in quartz veins, which could hint at overpressure or boiling events. We have a sample from Demirtepe deposit, which is a skarn deposit with garnet and tungsten-bearing minerals such as wolframite and bornonite. It's an uncommon tungsten-rich polymetallic skarn. When most skarns are copper and iron dominated in this area, this assemblage suggests unique fluid metal interactions. In image H, we have a sample from Kavakli Tepe, which is an epithermal to mesothermal gold and silver mineralization with limonite stained breccia. The coexistence of porphyry and vein-hosted systems in this area shows a significant exploration advantage. We have image E, Uludağ deposit sample, which shows a contact between two mica granite and skarn developed in marble. The bodinaged contact is a clear indicator of post-skarn deformation, which is a rare and valuable structural feature to observe in the field. Then here we have some microscopic tin and polished sections of different deposits. In image A, which is from Karapinaur, we see a textbook case of potassic alteration. We have large primary biotite grains, which are labeled as number 1, and smaller secondary biotite pseudomorphs, which are labeled as number 2. And you can see that how the original hornblende textures are preserved. This kind of dual biotite zoning is really distinct in other porphyry systems, and it's not something that you can see quite often in other porphyries. Then we have panel B, and here's something special. We have pyrite, chalcopyrite, and even a visible molybdenite inside the quartz vein. This clear multi-sulfide pyrogenesis underlines a well-zoned porphyry system with molybdenium commonly forming in deeper parts, and that's exactly what we see here. And then we have image C. Compare that to Gelemic, where chalcopyrite and pyrite are hosted in a phyllic altered granodiorite. The fine grain size and lack of molybdenite here hints at shallower levels of system, which are typical for copper-only porphyries. Then we have image D, And we have secondary biotite replacing hornblende, and it's overprinted by surfside and coarse sulfide waning. It's a classic overprint of philic over potassic, and the transition is so clean here. It's like watching time unraveling in rock form. Then we have image E, in which we have chalcopyrite, bornite, and covellite in one frame. Covellite is a kind of late stage mineral, and it's quite unusual here. It's often associated with supergene enrichment or highly evolved hydrothermal fluids. So this assemblage is a geochemical signature worth exploring. In image F, we have a sample from Moratere, which shows fine-grained pyrite, chalcopyrite in philic altered rock. And what makes this unique is that this deposit includes gold and rhenium, which are rarely found in classic porphyry systems, and it highlights a polymetallic nature of this mineralization in this deposit. And in image G, we have thin pyrite vein. We have a pyrite vein slices through feldspar and quartz. It's a sign of late stage sulfide waning, which post-date the host granodiorite. Density of sulfide vein can help us as a vector toward the core of the system in this kind of deposits. And in panel H, we have skarn sample, which shows a wollastonite garnet cut by bornite and chalcopyrite. And this skarn not only displays a textbook metasomatic texture, but also suggests a copper-rich endoskarn, and it's not always common in calc silicate environments. And in image E, we have a close-up of bornite nestled between wollastonite, which is a kind of interstitial texture, and it's often overlooked by but critical. It shows that mineralization postdates peak metasomatism event, aligning with fluid pulses late in the thermal evolution of the system. Here we have another image from the Gallhofer and his colleagues, which is a regional map. It tells the story of oblique subduction in southeast Europe, and it's a result of neotethid slab subducting at an angle, not straight down. And when that happens, the slab rolls back, pulling the arc westward, and that's why magmatism gets younger toward the northwest, and the same pattern that we saw in western Turkey. And there are evidence supporting the oblique subduction in this area. We have arc-shaped trend from Apusini to Srednogori area, which is consistent with oblique convergence and trench parallel extension. We have younging of magmatism toward the northwest. Magmatic activity becomes progressively younger from southeast to northwest, which is matching a slab rollback pattern. And just like in western Turkey's Diachronous arc evolution. Then we have presence of major transform faults, and faults like Mid-Hungarian and Sava They accommodate lateral tectonic movement, which is a hallmark of oblique subduction. We have slab rollback mechanism. The Tethyan slab is believed to have subducted at an angle, pulling the overriding plate westward, and it creates space for arc magmatism and migration. And we have some global analogs to this area, like Chile and Peru, the Andes, in which we have curved belts and trench parallel faults. We have low basin, LAU basin, in which we have arc migration and rollback from slab rollback dynamics. And in the Philippines, we have segmented arcs with strike, slip faults, and oblique subduction. And another evidence is mismatch between slab dip and arc orientation. The geometry shown doesn't support the perpendicular subduction. The misalignment suggests slab tearing or trench parallel extension, which is common in oblique setups. So we can see the metallogenic zoning here. The metal zoning here is not random. It's a fingerprint of the rollback, which is shaped by mantle flow, slab geometry, and cross-salt thickness as the arc migrated. And what you're seeing here is not just tectonics, it's tectonic storytelling through ore and mineralization. We have deeper intrusions, which are hosting copper molybdenum porphyries. We have shallower levels or more extended cross gold-rich epithermal systems. And why we have this range? Because as the slab rolled back, new space opened behind it in the mantle wedge, which allows stenospheric upwelling and metasomatized mantle melting. And this influenced both the chemistry of the magmas and metals they could carry. Okay, let's wrap up this article and connect the dots both in time and space. What we have seen is that porphyry systems don't just pop up randomly, they migrate, and that migration is controlled by tectonic processes, especially slab rollback and trench parallel extension. In the western Tethyan Eocene belt, we see this clearly, that mineralization moves westward through time, starting in the Tavashanli belt around 51 to 46 million years ago, then evolving through the Biga, Rhodope, and finally Serbo-Macedonian belt. Understanding this Diachronous migration is quite crucial. It means that timing is just as important as structure or geochemistry. And then we have uranium lead zircon dating and argon-argon alteration ages with rhenium osmium molybdenite ages, which allow us to pinpoint when these systems were active and, just as importantly, when they were not active. But time alone is not the whole story here. The structural framework, faults, thrusts, and extensional zones created architecture where magmas rise and fluids circulate. For example, at the Borsa district, it shows that how multi-phase stock, alteration zoning, and mineral assemblage can be decoded when placed in a proper tectonic context. So what does it mean for exploration? It means that we need to follow the slab, not just a belt. Watch how rollback moves. Look for changes in metal signatures from copper molybdenum to copper gold to lead zinc. They are indicators of evolving magma chemistry and depths of emplacement. And importantly, exploration doesn't stop at the outcrop. These systems can be deeply buried, but if we understand the tectonomagmatic clock, how time and space interact in subduction zones, we can predict where hidden porphyry systems might be waiting. In summary, integrating structure, geochronology, fluid chemistry, and tectonic is not just academic, it's a roadmap. And that roadmap can lead us to the next big discoveries. Thanks for watching.